So let's get back to our discussion on the spin-orbit interaction. So here, I would like to give a qualitative discussion first, and then there are a few pages that is slightly more quantitative. For the reason, as I mentioned, spin-orbit interaction becomes more important in recent work in physics. So we have mentioned that it is the motion of the electron that provides a magnetic field interacting with its own spin magnetic dipole moment. First of all, let's have a good sense about how strong that field is and what are we expecting as the magnitude of the effect. That is important in doing physics, okay? Realizing how important that term may be. So let's do a rough estimation. I need some E and M from you, electromagnetic field. Okay, so now, as I mentioned, the picture could be the electron is moving, but you can think of it as the electron is standing there. What it sees is the nucleus moving. So in any case, it's a plus, well, hydrogen is a plus E charge or minus E charge. So a charge moving is a current loop. So here, I try to make use of the electromagnetic theory, a current moving in a loop. You look it up, the result in Griffin's, the field at the center of the loop is given by this Biot-Savart law, mu 0, mu naught I divided by the diameter, 2r, all right? So we need to estimate the current. If the electron is moving with velocity v, speed actually, then the circumference is 2 pi r. And what is current? Current is charge passing a point per unit time. So you take a stopwatch, 1 second, how many charges passing by 1 point? So it is given by V divided by 2 pi r. That is how many rounds it will go through a point in a second, and the charge is minus G. So thereby, we have this for the current. Okay? We multiply by R divided by R, so become R squared is 1, nothing. Multiply by a mass of electron divided by a mass electron is 1, nothing. Okay, but we are very good at doing that. Now, you see a combination, which is the radius times the momentum, linear momentum, I mean, okay? And this combination is the magnitude of the orbital angular momentum, R cross P, but now just in the magnitude. Therefore, the current is related to how big the orbital angular momentum is. You plug it back to here. Obviously now, the internal magnetic field is proportional to the magnitude of the orbital angular momentum. And then we have a chunk of constants and 1 over radius cube. Let's estimate how big is this internal magnetic field. So you take any state, P state. We take P because we need L not to be 0. Okay, if you take S state, L is 0. We don't have contribution to the internal field. So let's take a 2p state. 2p state means this thing is square root 2h. Then we need a value for this. If you say 2p state, then I can take a 2p wave function. I calculate the expectation value. That will be a good representation of this number. So therefore, we need something like that. Okay. In a recent sample question, I think the TA used this too to get the relativistic correction example done. So here we need this. Don't worry, you look up tables for hydrogen state, they are standard results. So all we need here is this one. You are not supposed to remember that that is not the point here. We are talking about physics, okay? Here. But what I'm saying is that that can be done for hydrogen. And if you use this, the take-home message is you will get a field around 1 Tesla. Well, 0.7, a quarter, a 3/4. But you know, the field on Earth is just 10 to the -5 Tesla. And birds, you know, can find their path thousands of kilometers every winter, summer, winter, flying around based on this tiny magnetic field. So the field internal to the hydrogen turns out to be 1,000,000 times bigger, or at least 100,000 times bigger. Okay, so it is not a small field. The internal field of order 1 Tesla is something that we should look into. That's the take-home message. So here, I will start a derivation that gives the spin-orbit Hamiltonian, a spin-orbit interaction Hamiltonian, the part that we will use it as the perturbation. But I announced that it is just a partial derivation. It's not a complete derivation. For one reason, spin is a relativistic effect. Thereby, a proper starting point should be relativistic quantum mechanics equation, or the Dirac equation of an electron. Only when we start from there and then put in EM field, put in a Coulomb term, then we will get the full spin-orbit interaction term. Here, we will not do relativistic quantum mechanics. I will try as hard as I can using the idea of think classical and go quantum, just like what you did in many other problems, in order to get at the form of the spin-orbit interaction. It is educational because that is more physically transparent than start off with the Dirac equation and play with mathematics. So let's start. I need some electromagnetic theory from you again. So let's think about a 1 electron atom for simplicity. So we have an electron. I take it as taking an orbit, so I'm thinking classical. Notice the definition of the symbols. The electron relative to the nucleus is at a position vector r. Notice the direction, okay? Point to the place of the electron. The electron is moving with a velocity v. Look at the vector v there, okay? So it has a linear momentum. And then when we have r cross p, there is a pointing, you use this right-hand rule, you have a orbital angular momentum. Now, the interaction, of course, is Coulombic. So this nucleus is giving a Coulombic force on this electron. It's attractive, all right? So let's look at the electric field. Now, pay attention. We are talking about the electric field. Let's write down the electric field due to the nucleus. It is the charge of the nucleus. Hydrogen, you said is 1, but here just leave it general here. Then over R square, the direction, it is positive charge, thereby the field lines are radially outward. So it is in the direction of the position vector R. And the force on the electron is E and M. Q, E, all right, minus E, E. All right, and now because this is Coulomb force, we could write it as minus the gradient of a Coulomb potential energy. This is a force, this is a potential energy, not a potential. It's off by a charge, okay? Force is minus gradient potential energy. And it is this V goes into the Schrödinger equation. Because this is central force, depending on R only, the gradient takes on a simpler form. It is just ddr minus ddr, and then go in the radial direction. It is attractive, all right? So this is simple E and M. Now, the question is, what is the internal magnetic field? Here, naturally, we should start with the electric field, okay? And then we are talking about how could we get an expression for the internal magnetic field. So the left-hand side figure is the same as that on the last page. But now, let's take the viewpoint. Let's sit on the electron here, all right? And then look at the nucleus. So the nucleus is moving in the other way. So at this instance, the nucleus is moving this way, all right? When we call this V, this is minus V. And then I retain this R vector pointing from the nucleus to the electron. So it's the same R here, okay? So here I just want to emphasize this so that you can follow the cross product better under there. Now, from the viewpoint that the electron is sitting here and the nucleus is circulating around, there is a current density J. From E and M, J is the charge times the velocity. So it is ZE times minus V. Because we defined the V as that of the electron here, okay? Then use reference chapter 5. I checked it yesterday. You can find an expression for the magnetic field generated by a current density at a point R, okay? It is given by this. The slight current segment is here. So it is pointing at a place where you want to find the B field. Thereby, it is this expression, all right? So now I only use this E and M equation. I know J. I plug in the J here, all right? Very straightforward. So I plug in the minus ZE V. So this is my internal field. I collect the terms. I started to see minus V cross R. Thereby, it is R cross V. If I multiply a mass divided by a mass, I start to see R cross P. R cross P is the orbital angular momentum L. So we got things already almost done. The internal field goes like a trunk of thing, L, all right? Next, we want to explore further. What is the prefactor? What is the factor in front? All right? So I copy the result here and then further develop it. The first thing we notice is the following. There is a combination that looks like the E field. Let us look at the E field. It's here, okay? If I multiply a R divided by R, this R head R will be the R vector. And then I have a 1 over R cubed. So it is exactly this thing. This dashed circle is the E field that we had on the first page, all right? Thereby, the internal B field is given by 1 over speed of light square, E cross V. Now, for those who are good at special relativity, you started to see actually it's different viewpoints. We started off with E field, and you can regard that there is a B field generated if you are moving in the E field, okay? So here, we don't need special relativity. We are just using E and M, Biot-Savart law, and then we got the internal B field is given by this expression, okay? We are not doing mathematics, let me emphasize many times in this course. We want to get the physical picture. So I like to write this thing again here, and then what I'm doing is let the equation talk to you, all right? But you need to know how to read the equation first. To lead you through, I marked it 1, 2, 3 here. And you should read 1, 2, 3 in this particular order. So let me show you how. The equation is saying it is the electron's motion that V. Remember the picture I emphasized? It is the electron's motion, okay? So it is the electron's motion in the electric field provided by the nucleus that gives rise to a magnetic field that will act on the electron's spin magnetic dipole moment. Now, let me repeat. This is a very beautiful instant in learning physics, in my opinion. You have an equation, you should listen to what the equation says. It says, it is the electron's motion in the electric field provided by the nucleus that you can interpret it as a magnetic field at the position of the electron that it will interact with the electron's spin magnetic dipole moment. All right? If you look into the cross product, of course, the motion should be such that the cross product is not 0. Okay? Now, we have the E field, the motion, the E field is radially outward, the motion is perpendicular to it, right? Circular motion, perfect. The cross product is big. That will generate a magnetic field. This is how this beautiful equation is telling you the physics. All right? Appreciate what the formula says instead of deriving it, okay? You take it, understand what it says. Next, as I said, because spin-orbit interaction is now becoming very important in different areas of physics, in particular solid state and condensed matter physics, I would like to rewrite the answer in several forms. One form will appear in solid state physics more, one form will appear in atomic physics more. We have a big field called ultra cold atoms. Professor Wang Dajun is doing it, an expert in this field. And in that particular area of cold atom physics, you need the language of atomic physics, all right? So therefore, on this page, I just start with the 1 over c squared E cross V. I start playing with it. The first thing I play is multiply by 1, all right? But suddenly you see this is the force on the electron. The force on the electron is minus gradient of the potential energy function. The minus sign disappeared because I have another minus sign, okay? So this line, I turn it into the force experienced by the electron, then I can introduce the potential energy function V into the magnetic field expression. Second, I multiply by m, I divided by m. I want to pick up the linear momentum. Together, I start to see another form of the internal field. Equivalent, they are not different, they are equivalent, but written in another form. It is a chunk of constants, gradient of the potential energy function experienced by the electron, cross product into its linear momentum. This is an important form in solid state physics. Now, if we stop on this form, this V could be any form. It could be V as a function of X, Y, Z, alpha, theta, phi, all right? But for atoms, central force, this can be simplified to dV dr and the head R, the unit vector R, okay? And therefore, you start to see R cross P. R cross P is the orbital angular momentum. So at the end, you see what is determining the strength, the prefactor there for the internal magnetic field. It has to do with 1 over m(e) c squared. The sign of c squared here already saying something about relative motion, all right? And then it is the how rapidly the potential energy function is changing with R that matters. This dV dr will determine the prefactor. How big is that? Or how weak will be the internal field, all right? And then at the end, it is proportional to L, okay? You need P states to start with. L state will not, S state will not work. It will have no contribution, it works. So let me summarize. On this page, I start off with the known result, and then I turn it into 2 different useful forms. One is this one. For those who will do band structure, energy band calculation for your project, etc., you need this form. For those doing atomic physics, you need to know this, all right? So let us get into the Hamiltonian, okay? This B field, internal, will be thought into minus magnetic dipole moment of spin. We call this is the spin magnetic dipole moment. Therefore, you thought it into the internal field. this is proportional to L, thereby we get this S dot L term. We even know the prefactor, okay? The detail is that it has to do with the gradient of the V of R, okay? For rough thinking, just remember, the prefactor is not a constant. It is a function of R, all right? Now, there's an embarrassing moment. This is what I called partial derivation. This is as far as I can go. There is an additional factor of half that I cannot do it here. Well, someone can. I just skip it, okay? This equation 28 is the actual final answer of the spin orbit interaction term. I haven't argued about this half. These halves come from when you transform back to the frame that the nucleus is not moving, the electron is moving, there is an additional factor of half. Realizing that actually this frame are not so trivial. Circular motion is an accelerating frame. You need to do something called the Thomas precession, things like that in related to special relativity in order to get back this half factor. But the point is that I would like to introduce the key factors that determine the strength. All right, one tester and half tester, they are also already big. What I want to convey is that what are these factors here that determine the strength of the B field? So we will take equation 28 as the perturbation to move on. All right, so we get at the key result. But again, for the same reason that some of you may be doing solid state, may be doing condensed matter, may be doing topological insulator, some of you may be doing atomic physics. I would like to write down several equivalent forms so that you will not be scared later on when you read papers. Spin orbit interaction, all right? So let me complete the discussion here. Very often, we don't want to write it in the S spin angular momentum and introduce the Pauli vector, Pauli matrices. Remember, S is sigma over 2, so nothing. Become 4, and then you have this sigma dot grad V cross P. And remember, for 3 vectors, A dot B cross B, C, you have a lot of equivalent form. Another common form is sigma cross grad V dot into P. Okay? So here, this kind of forms are useful in solid state physics. Why? Here we do not use the central force, dV dr. For the reason that in a solid, there are many atoms, and the electron is living in the potential energy profile provided by not only by one atom, but by 10 to the 20-something atoms. So that will not usually be central force. Nonetheless, this form works, okay? So all it says is that it is the gradient, the change, the slope, well, in high dimension, 2, 3-dimensional, is the gradient of the potential energy profile that works, okay? That gives rise to an internal B field. So again, I will let the last formula talk to you. I'm copying this thing. Okay, so here again, play the same game. This is really important, okay? whether you are going into the field or just for physics cultural purpose. 文化呢個係重要嘅一點嚟。Okay, so let's listen to the formula. This is spin-orbit interaction term. Read it as 1, 2, 3. It says, when the electron moves, therefore it has a linear momentum perpendicularly that will give rise to non-zero cross product to the gradient of a potential energy landscape, then it will give rise to a magnetic field proportional to this grad V cross P that interacts with the electron spin. And that is the essence of spin-orbit interaction. Okay? Here, realizing that we need not rely on Coulomb. We just need an electron moving on a potential energy landscape that will generate some internal B field, free of charge. So we have two forms. This is good for atoms. Hydrogen, for example, we have a Coulomb central force, and this is good for general situation. So in an atom, you do have a Coulomb thing, nice, you can use this. Here, this is a picture for a solid. The crosses are the positive ions. There are some electrons. I focus on one. So this electron is moving in a potential energy landscape. The potential energy is provided not by one atom, but by many. All right. So as long as it is moving in a landscape, there will be a magnetic field generated. Okay. So if you are doing solid state physics, what happens? If you don't care about spin-orbit interaction, the Schrödinger equation will be kinetic energy term, potential energy term, time-independent Schrödinger equation. For a solid, this thing is periodic for the reason. If the electron position is here, it must feel the same thing as here because that point is equivalent to the other point. Do you see my arrow? Okay. And it's also the same as this point. This is what I meant by periodic. If you solve this, the allowed energies here will form bands, and they are separated by band gaps. And then you have metals, insulators, semiconductors. Now, usually in semiconductor business, it is important to include the spin-orbit interaction term. And that will be equation 1 for those who will be doing semiconductor physics. Silicon or something perovskite solar cell material, you need this, okay? Usually you need this spin-orbit interaction term to be included in your band structure calculations. Last comment on this spin-orbit coupling hematonia. Because of this dVdr term, okay, we realize that if the potential energy very rapidly, that will be equal to a bigger internal field. And that usually happens in the heavier atoms. That is to say, down in the periodic table. And that is why in recent years, many people play with elements in topological insulator things, rather heavy elements in their compound. All right. Last comment. We have been talking about electrons living in solids, living in atoms. But the whole point is electron has a spin half, and then there is a magnetic dipole moment, and it is charged. So if you think about proton living in a nucleus, proton spin half. It is confined to live in a tiny place called the nucleus, 10 to the minus 15 meter big, a sphere. Of course, the proton motion is inside the nuclear force, the potential energy profile provided by all the other protons and neutrons. So there will be an internal magnetic field generated acting on the proton's own spin half. Spin orbit interaction is also very important in nuclear physics. You don't need to learn it again and again. You learn it once and use it in many different fields. Okay? So if you go into nuclear physics, you also need that particular form, S dot L. In front, it is a function of R. Okay? So here is slightly longer than usual discussion on spin-orbit interaction. So let me see, there is a question sent in to me. Let me see what is it. If the electron is at rest at the start, then the electron will move only radial. Indeed. Well, but it is not an atom situation then. It is an electrostatic case. But we are talking about, we are focusing on spin orbit interaction in an atom. Okay, so we are thinking about the atom context. Okay. So now we have the Hamiltonian. We have the additional part. And now we are ready for a lot of things, right? Now, you must appreciate how we approach the problem. We first build up tools. Perturbation field. Okay? And now, we also build up background. What is the form of the spin orbit interaction? Okay, and more importantly, total angular momentum. Okay, now that is a long trip. Sometimes in physics, there's no shortcut. You really have to build up the tools and the background, and then things will become suddenly rather easy to do. This is one example. I hope you will appreciate the time we spent on building up all these things. So what is the question now? Without spin orbit interaction, you have solved this atom problem last term. Okay? You have been using the following description. For the spatial Schrödinger equation, you solve it in 3D, right? So you have three quantum numbers. Principal quantum number, L, orbital angular momentum, and the magnetic quantum number that we saw in Zeeman effect play the role of splitting the lines, the levels. And then Pauli said there's a fourth number. Actually, there's fourth and the fifth number. Electron is spin half, S is half always. Therefore, we usually skip that. Then the Z component can be plus minus half. We skip this, then we have 4 numbers. Okay, I give a bracket here just to remind you, actually in complete form, there are 4 or 5 numbers. And this is what you did. In general, for central force, the eigenvalue will depend on N and L. In general, 2s is different from 2p, except in hydrogen atom. 2 sections ago, we learned that this is one description, but we can add orbital angular momentum to spin angular momentum to become total angular momentum and its Z component. So this is another description. They describe the same set of states, no more, no less. It's just linear combination of one another. Therefore, if it is this same atom Hamiltonian, they will have the same eigenvalue, just like the 2p state we have been using as example. The 6 states, same energy, 2p, linear combine them into JMJ, same energy, 2p. But the question now becomes, I have a spin orbit interaction term. The Hamiltonian becomes this. What happened? So the mathematical situation becomes the following. I have one description, previous description. They are the same. One way, another way to write it, plus minus, up, down, spin, okay? But you mix them, linear combine, you can use the JMJ description, but no more, no less. 6, also 6, okay? If it is H0 only, they are both good. But with spin orbit interaction included, one set is better than the other, all right? This total thing is much better than the other because it turns out it will make the first order perturbation theory very easy to do. Let's see why. Here is the magical moment. We now know the spin orbit interaction goes like S dot L. The prefactor is a function of R, rather complicated, gradient of V or dV dr1 over R, things like that, okay? We argue it, and then now we go quantum. So this thing becomes operators, okay? So we need to handle S dot L. When you see this term, immediately in your mind, start thinking about total angular momentum for the following reason. You consider J square, which is J dot J. Immediately, you know, you pick up a 2 L dot S term. L and S commute. They operate on different coordinates, okay? So therefore, S dot L can be written in J square minus L square minus S square divided by 2. Okay, this is the key step. And this is the key reason why we spend a few hours to learn all this total angular momentum stuff. All right. So suddenly the last term can be expressed as J square L square S square. These are the magnitude square of 3 angular momenta, total, orbital, and spin. And we know the answer, okay? So the new Hamiltonian becomes atomic part we know how to solve, and this thing. This included the spin orbit interaction. So now Let's do first order perturbation theory, the simplest thing we can think about. Now, some of you who are very good may think, oh, we should use degenerate perturbation theory. Good for you. But then even better, you will see, we don't need that, because when we use now, the following 30 seconds is slightly technical. If you don't follow, don't worry, we will get to the answer. Some of you may think we need degenerate perturbation theory because P states, the 6 states are degenerate. We should have a 6x6 matrix, single out, do it, right? Good, very good, excellent. You learned it right. But we are going to see, if we first change the basis to total angular momentum JMJ description, this 6x6 is diagonal by itself. There's nothing for you to worry about in the off-diagonal term. So we don't need to worry about take the 6x6 out, doing it exactly. We already did it exactly, okay? Now go back to the normal discussion. So first order perturbation means the following. Take the unperturbed state, find the expectation value, okay? Just to remind you. Now we switch bases first. We will use the JMJ description. Remember 5 number, no more, no less. We switch to N, L. The magnitude of the orbital is still there. The magnitude of spin is still there, but JMJ instead of MLMS. Okay, that is the change. Therefore, the unperturbed energy is still NL labeled. Just to remind you, when you see J square operating on this, it pick up this eigenvalue. When you see JZ operate on this, you pick up MJ. When you see L square operating on this, it identify the L. When you see S square operating on this, it find the S, and it is the boring half. Okay, so it is this. Okay, so ready, go. Perturbation, expectation value. The perturbation term has J square, looking for J. L square, looking for L. S square, looking for half. All has H bar square, okay? But don't be too happy. There is a radial function, but this function has a radial function, capital R and L of R. You still have an integral to do. I will call it the expectation value of this thing, okay? Just a number. Now suddenly we are done. Do you see? No more work. You should appreciate this particular step. You should appreciate your effort in building up the background, okay? So suddenly we know the shift in energy will depend on J, all right? What does it mean? For the P states, there are 6 states, right? But we know there are 2 values of J. J can be 1 plus half or 1 minus half, you see? And these 2 multiplets, different J values will have different shift. The 6 states, okay, will become 4 and 2. They will take on different energies. Do you get the point? That is spin orbit splitting. Spin orbit splitting. Do you understand? Depending on the J now. Very simple answer. Okay? So here I illustrate the effect. This figure, I blow it up for you to see. Okay, remember, the internal field is 1 tester, but it's multiplied into a ball magneton for the splitting. Okay, so S state, no effect because J is half. J is half, L is 0. When J is half, this cancel out the term, all right? So no shift. P state, 6 states there will split into J equals half and J equals 3/2. Behind this, there are 2 states. There are 4 states. The degeneracy is partially removed, not completely, partially, okay? 6 become 2 and 4. How about these states? You have to work it out. It becomes 3/2, 5/2. It becomes 4 states and 6 states. Okay? Now, the splitting here is exaggerated. It is Bohr magneton times 1 Tesla, so it's about 10 to the -4 eV. All right? That compared with the ground state to the first excited state, n equals 1, n equals 2, this is 10 eV. Nonetheless, we happily obtain the effect. P state will split into 2 sets. J half, J is 3/2, okay? And that is observed in the spectroscopic data. So I think I have to stop here today, and then we are getting to the very interesting effect down there, all right? So next time, we will work out more effect of it, but then we also need to include the previous relativistic correction. Then we have a formula for the correction in hydrogen. We want to compare with real data and then introduce a tiny bit that we cannot explain within quantum mechanics. That is called Lamb shift. That has to do with quantum field theory. We will just mention that tiny bit, and then we will go back to the Zeeman effect one more time, okay? And understand the enormous Zeeman effect. So long for now. I will stay on for some of for questions that you may have.